Okay, it's like every day we get like a 3, 2, 1 action. It's exciting. We'll start things off by reviewing yesterday. So yesterday we reviewed a couple definitions. So the first definition we learned was the word factor. Who remembers what the word factor meant? Somebody. What's a factor? I was like, what's a factor of 6? 3. 3 would be a factor of 6 because 3 can divide into 6, right? Factors are numbers that divide into something. So when I ask you for the factors of 6, you would write all the things that divide into 6. Awesome. The next definition we learned was the word prime. So we talk about prime numbers. Prime numbers are, numbers with only 2 factors and exactly 2 factors. So the number 1, remember, didn't count because the only number that divides into 1 is 1. And number 0 doesn't count because technically we can't divide 0 up into anything. So prime numbers would be like 2, 3, 5, right? Numbers that can't be divided by anything else. Awesome. Then what we did was we did something called prime factorization. We kind of blended the two ideas together. And we took numbers and we broke them up into only prime numbers multiplied together. And we called that product of prime numbers. That's what we're going to review right now. So we're going to write 48 and 72 as a product of prime factors. Our strategy is to use a tree, and I use a prime factorization tree. The way the tree works is you write the number you want to prime factorize, you break it into 2 numbers that would multiply to be 48. One of those numbers preferably being a prime number. So for instance, 48 divides by 2, and that would give me 2 and 24. That's my 2 numbers that multiply to be 48. When I'm making my tree, if a number is prime, I circle it. And I say that I'm like done that branch of the tree. 24, however, could continue to be broken up. So I would break it up to become 2 and 12. Then I would break 12 up to be 2 and 6. And then I break 6 up to be 2 and 3. Both of which are prime, so both numbers get circles. Now my tree is completed because every branch ends with a circle. The circled numbers, these guys, represent 48 as a product of primes. So looking at this, I have 1, 2, 3, 4 2s. So that'd be 2 to the power of 4. Times 1, 3. This is a product of primes. 2 to the power of 4 times 3. You go ahead and you try to review 72. So try to write 72 as a product of prime numbers. I took 72. I wanted to write it as a product of primes, so I used a tree, right? This is not a product of primes. This is prime factorization. The product of primes comes from all the circled things multiplied together. Because when I was done my tree, I had 3 2s, I said it was 2 to the power of 3. And I multiplied it by, it was 2 3s, so I did 3 to the power of 2. This is my product of primes. Okay, I took a number, I broke it down into a product of primes. That's a multiply by 3, 2. But again, this new board doesn't really like it. Let's see if that works. Yeah, it does these bubbles. Pretty sweet. There, that looks a little bit more like it's supposed to. Fantastic. So that's what we did yesterday. Today what we're going to do is we're going to use this stuff to calculate a couple things. We're going to start off by calculating your greatest common factor. Before we get into difficult greatest common factors, we're just going to discuss what a greatest common factor is, and we'll do some easy ones. So a greatest common factor, if you break down the words to that, factor means numbers that divide into something. Right? Common means it's shared among everything. And greatest means the biggest number. So if you think about greatest common factor, that means largest number that can divide into everything that you're given. So for instance, if they say, what's the greatest common factor, they use the word GCF, of 8, 16, and 20. They're asking what's the biggest number that divides into all three of those. And the biggest number that divides into all three of those would be 4. And I can do that one just by looking at it because they're small numbers. And I'm like, well, what divides into 8? What divides into 16? What divides into 20? And I just take the biggest one that all of them share. That's a GCF. So looking, we could do a couple more. If I look at 15, 25, and 35, and I say, what's the GCF? The biggest number that would divide into all of those would be 5. If I look at 18 and 20, and I say, what's the greatest common factor there? I think it's only 2. Can anyone think of a bigger one than 2? I can't. 6 goes into 18, but not 20, so I'm pretty sure it's just 2. Last one, you have 36 and 54. That's a little bit trickier. So try to write out the numbers that can divide into them. Okay? And you might be surprised that there's a bigger one than what you think there is. So I'll write out all the things that can divide into 36. In red there, that's all the things that divide into 36. You can do the same thing for 54. It's going to be hard to get used to my eraser now. Okay, so I've now written out all the things that divide into 36, all the things that divide into 54. And if I'm looking for the greatest common factor, these things share 2, they share 3, they share 6, they share 9, they share 18. The bigger the number, the more things that are going to be common. And a lot of them aren't obvious. 18 is not an obvious one that divides into both of those. Right? So that's why it might be wise to have a strategy for bigger numbers. When it gets to the really big numbers, like we're about to, that's where prime factorization is going to come in handy. Because it might be easy to figure out, yeah, they both share 6 or they both share 3, but it might be really hard to figure out the greatest number that divides into both of them. That's why prime factorization exists, because then we don't make mistakes. We can use that tool to always get the right answer. In our case, this one would have been 8. All right, looking at how prime factorization works, we're just going to skip down to an example. Because I have a little bit of a different strategy than most people when it comes to getting the GCF of big numbers. So I look at this question, it says use prime factorization. Prime factorization means the tree. Okay, so use the tree to determine the greatest common factor. of the numbers given. So I need to do a tree for both of these. I'll do them quickly. So for 90, it would break up to be 2 and 45. 45 would break up to be 3 and 15. And 15 would break up to be 3 and 5. That means after prime factorization, I get 2 times 3 squared times 5. You don't need to worry about being able to do the tree right now. You should be decent at it because we practiced it a little bit. Just make sure you have it written down. I'll also do the tree for the 225. 225 divided by 5. It's a tricky one. 45. That divides by 3. You get 15. Divides by 3. You get 5. So that gives me 3 squared times 5 squared. Awesome. I'll give you a second just to copy those down so you have the same prime factorization as me, and you've written your things as a product of primes. That's the important part. Writing it out as the 2 times 3 squared times 5, and then the 3 squared times 5 squared. All right. To use this to find the greatest common factor, what we do is we look at our 2 answers that we hear, our 2 product of primes. And I look to see what prime numbers I have. So I've used the number 2, the number 3, and the number 5, and then the 3 again and a 5 again, right? So 2, 3, and 5 are the 3 numbers I've used. 2, 3, and 5. And I write those down. Those are the 3 prime numbers I used in my trees. The next thing that I do is I have to pick exponents for all 3 of these numbers. For greatest common factor, the exponent that I'm going to use is the lowest exponent that ever happens for that number. So for instance, let's look at the number 5. In the red tree, the exponent on my 5 is a 1. In the blue tree, my exponent is a 2. The lower number would be 1. So I put 5 to the power of 1. Now I need to pick an exponent for the number 3. The lowest exponent that I use on a 3, I look at my red tree, I use the exponent 2 on a 3. The blue tree, I use 2 on the 3, so the lowest exponent would be 2. So I have 3 to the power of 2 times 5 to the power of 1, and I still have my 2 that I need to pick an exponent for. Picking the lowest exponent for the 2 is tricky. Because if you look, it looks like the lowest exponent is 1, correct, from the red tree? When in reality, the lowest exponent is 0, because there is no 2 in the blue tree. So this means there was 2 to the power of 0 in the blue tree. Lowest exponent would be 0. If you multiply these things together, so you put 2 to the power of 0 times 3 to the power of 2 times 5 to the power of 1 in your calculator, that will give you your greatest common factor between your 2 numbers, 90 and 225. When you actually calculate that, you should get 45. So 45 is the greatest common factor between those 2 numbers. The first couple of times you see it, it's kind of confusing. You're like, whoa, where's he picking these numbers from? And then you start to realize it's just a pattern. And it's easy to follow along with that pattern. It's not so bad. But the first couple of times, it can definitely be a little, whoa, what just happened? Okay. So if I wanted to find the greatest common factor between 154 and 198, I need to write them as a product of primes. On the sideboard, 154 becomes 2 times 7 times 11. 198 on the sideboard becomes 2 times 3 squared times 11. Right, those are my two product of primes for 154 and 198. Our goal is to find the greatest common factor using this information. Anybody else see that? Some water just dripped out of the roof. That's freaky. Anyways, to figure out the GCF, you have to figure out which numbers you used in your prime factorization. Looking at my prime factorization, I used the number 2. Right? I used the number 3. I used the number 7. And I used the number 11. Those are the numbers I used. You then have to pick exponents for each one of these numbers. For greatest common factor, you want to choose the lowest exponent. The lowest exponent for 2. What was the lowest exponent I used on a 2? 1. Okay. This one had 2 to the power 1. This one had 2 to the power 1. The lowest exponent would have been a 1. I look at the number 3. And I say, what's the lowest exponent I ever used on a 3? And this one's tricky because it looks like it's 2, but in reality it's 0. Because I never used it on this number, the black side. So that means it's 3 to the power of 0. 7. The lowest exponent I ever used on a 7 was 0. And 11, the lowest exponent I ever used on 11 was a 1. If you put this into your calculator, 2 to the power 1 times 3 to the power 0 times 7 to the power 0 times 11 to the power 1, you will get that 22 was the greatest common factor between those two numbers. This is a foolproof way, and it'll work for as big a question as you can get. So if you're using, I could ask you 10 numbers, they could be in the thousands. And all you'd have to do is make a tree for each number, break it down, choose the lowest exponent for each number that you used, and you would get the answer. I'll let you try this one. So I'll give you a little bit of time. 245, 315, and 770. If you also want to try B, feel free. There's just bigger numbers, and there's 4 of them. But I want everybody to try A. And I'll also put my answer for A up on the board. This one, I've broken it into colors. So 245 is the red tree, 315 is the blue tree, and 770 is the green tree. You'll notice that underneath each tree, I write it as a product of primes. So one of the biggest mistakes I think we find is that people use prime factorization. They know how to do the tree, and they forget to write it as a product of primes underneath. And that part is important, right? Because that's how you know how to pick your exponents. So make sure you're writing it that way after. The next thing is that you need to pick the numbers that you've used in your product of primes. So for instance, I've used the number 2. I used 2 here, so I use a 2 there. I used a 3, so I use a 3. I used a 5. In fact, I used a 5 in a lot of spots, so I used a 5. I used a 7, so I put a 7. I used an 11, so I put an 11. Right? That's how I'm choosing those numbers. They're the numbers that I used in my product of primes. Then I pick an exponent for each one of those numbers. It's the lowest exponent that you can find. For 2, the lowest exponent I used could have come from this one, which is technically 2 to the power of 0, or this one, which is technically 2 to the power of 0. The next number would be 3. This one technically has a 3 to the power of 0. We just don't write it in there, right? But that's the lowest number we would have. If we look for 5, we have 5 to the power of 1, 5 to the power of 1, and 5 to the power of 1. So the lowest exponent I used was a 1. For 7, I have 7 to the power of 2, 7 to the power of 1, 7 to the power of 1. So the lowest exponent I saw was 7 to the power of 1. And then there was only one of the trees with an 11. These guys were missing the 11. So they're technically 11 to the 0. The last thing that I see people make a mistake on is they do all this work, and they do a fantastic job, and they don't put this in their calculator. Right? So if I asked you, what's the greatest common factor? What's the largest number that divides into these three things? And you responded back with 5 to the power 1 times 7 to the power 1. That'd be a crazy conversation we just had. Right? If I ask you what's the largest number that divides into something, your answer should be a number. Right? 35. 35 is the largest number that divides into all three of these. You wouldn't say this big string of calculations to it, right? So make sure you're actually calculating the GCF, which is 35. Fantastic. We're not going to do the next one because it's just the same thing over again. It's just bigger numbers, right? But it's good practice for you if you want to on your own time. We are going to move on to something called lowest common multiple, right? I like to call it an LCM. I think they'll probably use that terminology too. Yeah, there it is, LCM. Okay. So lowest common multiple means LCM. We're going to break down the words lowest common multiple to know what it's asking us for. So lowest in math would mean smallest number. Right? Common means it's shared among all things. And multiple means things that your number could multiply to become. So multiples are getting bigger. So for instance, the multiples of 6 would be 6, and then another 6 would be 12, times another 6 would be 18, plus another 6 would be 24. Right? These are all multiples of 6. It's basically what happens when you count by sixes. If I said what are the multiples of 8, you do the same thing, you're just counting by 8. So it'd be 8, 16, 24, 32, 40, 48, and so on and so forth. That says 5. I'm pretty sure that's a typo. 8 doesn't multiply to become 5. If you then look at the common multiples, these actually have a few common multiples. They both multiply to be 24. They both multiply to become 48. And if you kept going, you would find more and more and more. There's an infinite number of common multiples. That's why they only are concerned about the lowest common multiple, because you'll never find the greatest common multiple. It goes on forever. Right? Those numbers are huge. So your solution to lowest common multiple would be 24, because that's the lowest number that they both could multiply to become. Awesome. Again, with small numbers, you can kind of do it in your head sometimes. So they gave you a couple numbers here. They gave you 5 and 7. If we want to talk about the lowest common multiple between 5 and 7, you would count by 5s. Right? So 5, 10, 15, 20, 25, 30, 35, 40. And then you count by 7s. 7, 14, 21, 28, 35, until you find one that they both would multiply to become. In our case, they both could become 35. And that's the first thing that they both could become, or the lowest number. If you look at B, you have 3 numbers now. You have 10, 15, and 20. The lowest common multiple means it's going to be a number they could count to become. So you have like 10, 20, 30, 40, 50, 60, right? For 15, you have 15, 30, 45, 60. For 20, you have 20, 40, 60. The lowest one they reach is 60. The last one's a little bit trickier. Right? The first two are actually pretty tricky too, but the last one's the trickiest one. So you have 10, 12, and 14. If you had one with small numbers like that, you could still count it out. You might need to make a list. It's going to be a little bit hard. So for 12, I would go 12, 24, 36. Oh, maybe not. Whoa, what did that just do? What does that mean? 12, 24, 36, 48, 60. And I hope that's going to work. 14, 28, 42, 56. It's not going to work, man. Keep going. 70, 84, 98, 102, 116, 130. All right, let's hope that one works. It doesn't. Woo! If you kept going, you'll find it eventually. I can't keep writing numbers though. Plus, what am I adding? 14s? And I'm gonna keep going until I find a number. I'm just adding 14 in my calculator. And you can see this is like a tedious process when you do it this way, but it would work. 200, I think is gonna work. Oh, it does not. Holy man. We're gonna abandon doing that, but it's a good lesson, and that's really hard, right? And you technically could do it. Your list is just going to become really large, and it's going to keep on going and keep on going. So there's got to be a better way, right? Especially when the numbers get bigger and more complex. The way that we're going to calculate LCMs is prime factorization. We're actually going to follow the exact same steps we did for GCF. And the only thing we're going to change is the exponent that we pick. So for lowest common multiple, we're going to pick the greatest exponent. So it's kind of opposite. Greatest common factor, you pick lowest exponent. Lowest common multiple, you pick greatest exponent. I'll show you how it works. We're going to just skip over to the next page. We'll prime factorize these things. When you prime factorize, we'll start with 15. It'll become 3 times 5. And when you prime factorize 35, it will become 5 times 7. Okay, so I've already done it for you. You don't need to worry about drawing the true. Just like GCF, you then look at your prime factorization and you write out all the numbers you used. You used 3, you used 5, and you used 7. And you need to pick an exponent for all 3 of these things. For LCM, you want the greatest exponent. It's opposite. Greatest common factor, pick the lowest exponent. Lowest common multiple, pick the greatest exponent. In our case, looking at this, the largest exponent I ever used on a 3 was 1. The largest exponent I ever used on a 5 was 1. And the largest exponent I ever used on a 7 was 1. So I would go 3 to the power of 1 times 5 to the power of 1 times 7 to the power of 1. And you should get 15, 30, 60, 90, you get 105. That would be the lowest thing that both of those numbers could multiply to become. Awesome. We'll do one more together, and you can do one more on your own. I'll do my prime factorization on the side. So again, awesome. So we did our prime factorization on the side. Can I move this? I can't move it. That's frustrating. Well, away she goes. just want to give myself some more space. So if I look at 126 and 441, I broke them down on the sideboard. 446 or 126 became 2 times 3 squared times 7. 441 became 3 squared times 7 squared. If you want to pick the lowest common multiple, you write down every single number that you've used. I've used 2, 3, and 7. And then you pick exponents for all 3 of those things. Because it's LCM, we pick the greatest exponent. The greatest exponent for 2 would be 1. The greatest exponent for 3 would be 2. And the greatest exponent for 7 would be 2. When you actually calculate that, so 2 to the power 1 times 3 to the power 2 times 7 to the power 2, you get 882. That's the lowest common multiple between those two numbers. That'd be a hard one to get to, right? That's a big number. Okay, so just remember, you take it, you break it down using a tree. You write it out as product of primes. That's what this is. Then you use the highest exponent or the greatest exponent because you're looking for LCM. You can try the last one. This is our last example. So 22, 154, and 198. Go ahead and give it a shot. I'll give you lots of time. Okay, there we go. Anyways, so I got all 3 trees there, so I've written them out for you so you can see them. So for 22, it broke up to be 2 and 11. I then write it as 2 times 11. The red tree is 154. It breaks up to be 2 times 7 times 11, right? All the branches. I think the biggest thing people will make mistakes on with their trees is that they think things can't be divided that can be divided. So for instance, they might break it up into 2 and 77 and then stop. Like, I can't find anything that divides into 77. And sometimes you just have to guess and check prime numbers. So if you remember your first 10 prime numbers, that'll help you out. Okay? Usually numbers will break down into small numbers like 7, 11, 5, stuff like that. So don't give up too quickly on your trees. The purple one, I have 198. It broke up into be 2 times 3 times 3 times 11. So that's 2 times 3 squared times 11. Awesome. I wrote out all 3. You'll notice I then in black, I wrote out the numbers that I used. So I used the number 2, 3, 7, and 11 somewhere in my tree. I used all those numbers. And then I chose the highest exponent, greatest exponent for lowest common multiple. The greatest exponent I ever saw on a 2 was a 1. The greatest exponent I ever saw on a 3 was a 2. The greatest exponent I ever saw on a 7 was a 1. And the greatest exponent I saw on an 11 was a 1. I then actually calculate that big thing I just created. Okay, so I put this in my calculator, and I get 1,386 is the lowest common multiple. Awesome. How many people got that? Good. Decent number. That's awesome. The rest of this stuff, so it's about prime factorization of perfect squares and perfect cubes, is the exact same process of what we just did. Nothing changes. So we're not even going to review them because it's literally just more practice, and I think that we're good on our practice for our lesson now. So you can skip forward to the assignment. So the practice questions start at the bottom of page 11. Page 11? Yeah, bottom of page 11. And you can start there, practicing greatest common factor. If you don't need to use the tree, you don't need to use prime factorization, and you can just see it, feel free to just answer the question. If you need to do the tree, you'll see they gave you some space where you can actually use the tree system. Awesome.